thing about what the basic numerical scheme is, uh, and most of you have heard the name simple, in the Fluent. And this scheme is used not only in Fluent, but it is used in almost all the solvers. So whether it's CFX or COMSOL, is a very, very powerful and important scheme, and you can write your own code. You can try to write in 1 dimension, 2 dimensions, and somebody is doing the flow in a cavity, it is very easy to write this code. If you want to know the basics and you are interested in doing that, you can try that. Okay, it's not going to be a research problem, but it is going to be a good experience to try and try to see, whether you can do some tutorials in Fluent. So this gives you some basic idea about that black box that we discussed, and there is no difference in the single phase and multi-phase in the Eulerian and Eulerian model. Now, later on, we will also going to talk about the Eulerian Lagrangian model, which is important when you have a solid particle, like the core particles in air for combustion. Then those particles are moving, and so there's a two-way interaction, and we will discuss that later. So right now, I think that what I have described to you is good enough, and there are some summary slides, and they can tell you some information. Even if you don't pursue it, at least you should know that what it is all about. Now, this thing is purely multi-phase, and this is something I think there might be written in Fluent manual what they use. Like everything that I showed you before, that is not the only way to solve the problem. There are 10 different methods to solve the problem. Okay. So similarly, for volume of fluid method, there are number of ways you can solve that problem. Okay. So I will show you, 2 or 3 ways, and so Fluent has one of those ways to solve the problem. And in their manual, it's possible that information is there, but I will again capture, some of the essential idea that how it is done. Okay. So it may be beneficial to do this. So now this is the volume of fluid method. Okay. So this is pertaining completely to the multi-phase flow, and there is a small part of Fluent that has this. So what you see here is that what is the definition of VOF? It's known as VOF, and this is based on a paper actually published in the Journal of Computational Physics sometime I think in 70s by Hurt and Nichols. So now you have gas, it's a simple model, it's shown there a sketch, and there's some liquid, and this is the interface. So this yellowish area is the interface, and this is the one that we want to capture, and this interface can deform. That is the most interesting thing. So if you saw some of the videos in the presentation that a bubble is moving as a circular bubble, and when it moves up, because of the forces that it is experiencing, that is the surface tension force, gravity force, etc., it deforms. So this interface is going to deform, and that is you must capture as it deforms during the process of the interaction. So this is a definition. So this is alpha is a standard definition and notation that is used. So this defines the gas and liquid interface. So which means that if alpha is 0, you are in the blue part only. If alpha is 1, you are in the red part. And if you are alpha is 0 or 1, between 1, then you are somewhere in the greenish yellowish part. Okay. So it can be half, it can be 1/4, it can be whatever. All right. So the question is that as this bubble, or let us consider this as a bubble in one of the videos that I showed you, and it moves and it deforms, in time, you have an interface that is deforming. How do you capture that interface? How do you calculate that interface? So that is the volume of fluid method. Okay. How many of you, as I asked before, has come across this and has used it in calculation? Has anybody done that? Okay. So there are a few people. How many of you know the theory behind it? So it may be useful to see what it is. It's a very simple theory. So now the density gas notation, this is liquid. All right. So there are two phases, liquid and gas. So it's straightforward here. Now this is the interesting slide that is different, from the standard slide. So you have mass conservation, which is a standard conservation of mass equation, and the momentum conservation is different. So momentum conservation, you have the convection term, inertia term. Then of course you have the pressure term, and then you have the viscous term. Okay. So and then you have the gravity. So all these terms that you have are a part of a single phase flow. This is the term that makes it a multi-phase. So what you see here in this term, which is called a surface tension force. You have gravity force, the pressure force, the viscous force, and this is the mass times acceleration. And so you have sigma, which is a notation for the surface tension. Kappa is the curvature of the fluid phase of the bubble. Eta J, eta F is the normal to the interface. And this is a delta function, which means that this becomes important when this coordinate x approaches the interface, otherwise it is 0. So this is expressed as a delta function, and this is the surface tension force, which makes the momentum equation different for a multi-phase flow than in a single phase flow. All right. So now we are bringing something which is not there in a single phase calculation using the any of these code. Of course, these are the notations, remember. So this is most important to remember is the kappa at the interface, the normal at the interface. Of course, alpha is the liquid volume fraction, 1 minus alpha is the gas fraction, and this is the location of the interface. And delta function, it becomes 1 or a 0 for a sharp interface, right? If you don't have a sharp interface, you can fudge it, all right, which one I will show you later. But right now, this is a sharp interface. Now, this is the thing that is the volume of all fluid method basically uses to determine the interface. So this is the contribution actually which was done by Hurt and Nichols in JCP, Journal of Computational Physics. I have that reference. I don't remember the date. It's somewhere in 70s. So that was a very breakthrough work, that the interface is defined also by a convection equation. So this is advection convection equations like a continuity equation. And so this is a gradient of this fluid fraction, and this is the movement. And so the calculation of alpha as a function of x and t defines the interface. And once you have that, then you go back to this equation. Once you have the interface, you have nj, you have kappa j, you know the sigma, you can calculate this, and then you can calculate the velocity field, the pressure field, using the same simple algorithm, and you are done. Okay, so that is the whole philosophy. So now the question is that how do you solve this? Of course, this is a simple advection convection equation, is transport equation. You use any of those algorithms and you can solve it. All right. Yeah. Now the trick is that what this interface is moving and how is your grid. You see that you have got some grid using ICM or whatever you have. So suppose you have a you have a column, cylindrical column that I showed you. You created some grid, very simple. That interface is not going to be, it will be all over the place. So it will be, suppose, a curvature. So it will be, part of it is one cell, part of it is another cell. So how do you take that grid information and be able to apply the do the calculation for this particular equation in which this interface is moving over the grid? That is the most difficult part, and that is the critical part of this calculation. Once you figure that out, you're done. It is a very simple equation. Okay. So now this is what it says. So let us say that this is the interface. All right. So how do you first of all represent this interface? Of course, you can represent as a staircase. So you have this, you can have this staircase. Because it is not a very good approximation, as you can see it. All right. Now you can also do this linear little changes. So this is like representing it as a linear representation. This is called PLIC, PLIC. So it is called the piecewise linear interface calculation. PLIC, piecewise linear interface calculation. And so what you have here is that this is the easiest one. Of course, if this is your original grid, by the way, which is a square or rectangle. And so if you have a more finer grid, these guys will become more and more closer to the interface. The next one you can do, if you want to be more closer with a same grid, you can go to quadratic. So instead of linear, you can have a quadratic function. Okay. And if you are so inclined to do research in this area, you can take a cubic. But you can get a very good answer with this. So not only the fluent, but every multi-phase flow code, including MFix and some other ones, Barracuda and so on and so forth, they use only PLIC. This is very good, that can give you a good answer. Because if this rectangular grid is good enough, that is good enough for a linear algorithm, and it is very easy to implement. So unnecessarily don't add more complications. Okay. So this is the numerical representation of the interface. So now you will see how do you basically deal with this. Again, your grid is the same, all right. So what you have is, this is the original equation of Hurt and Nichols, d alpha dt plus the velocity vector u times this gradient. This is a standard form of even the continuity equation with minor changes, and you expand it in 3 dimensions, then you get, so you have a scalar. So you have a scalar for alpha, which represents the fraction of fluid, liquid, and 1 minus alpha is the gas, the way we are doing, and this is our rectangular grid. And so this 0 is the cell center, because we are using a finite volume, and so ijk is a 3-dimensional, in 3 dimension is the cell center, this is cell center I plus 1, etc. And these are half location. So when we discuss further, this is called the center of the volume or finite volume, and this is called the face of the finite volume. This is just standard way of talking about it. And this is the interface. The question is, how do we capture this interface? So if you want to really understand it, first do 2 dimensions, and then of course, then do the 3 dimensions. What happens if it is in 1 dimension? I told you in 2 dimensions this is the figure, right? In 3 dimensions it will be some kind of an inclined plane. What happens in 1 dimension? Hmm? 1 dimension is going to be a point. Nothing much is going to happen. So you don't have to worry about it. All right. That point may move. The movement of a point is much simpler, and in terms of there is no deformation. Deformation is just a simple movement. The reason I ask these questions is so that I am sure that I at least feel assured that you are awake. Okay, this is a very trivial question. All right, so this is what we need to calculate with this equation. So what do? A simple calculation. There is nothing there. So in 3 dimensions, this is the time derivative alpha n plus 1 is the time index minus alpha n divided by delta t. And then we are again applying it at the interface like I plus half, I minus half in the x direction, j plus half, j minus half in the y direction, and k plus half and k minus half in the z direction, and that's it. Now, if you have this algorithm, what is it called? It is explicit because on the right hand side everything is known. And so, this is the easiest way to do it. Unnecessarily don't make it implicit, because implicit means that you are going to have a matrix, and if it is a big grid, you are going to make your life miserable. So, normally explicit is going to give you a very good answer, and this is all you do. And so, now these guys, you know, we can average it on the, just like I showed you here, you just simply average all these quantities at the middle points, and that's it. So you can have interpolation of the cell center to cell face. All right. Now, what kind of interpolation will be okay? You can go as fancy as you want, but a simple linear interpolation is good enough. Don't become quadratic and cubic, etc. So simple linear interpolation going from cell center value to the face center value is just good enough. You cannot take the cell center value to be the same as the face center value. Then everything will fall apart, because then you are not allowing for variation. Okay, so you just take a linear value, and that's good enough. Okay, so these are the things that are important to remember if you are doing your own coding. But even if you are not, that is what the Fluent has. And I keep saying Fluent, that is every code has. Okay. So this is the equation that you need to solve. So of course, this discretization is, what is the order of accuracy, by the way? Second order. So naturally, you know, if your grid is, you know, not that fine, it will create a lot of error also. All right. So those things you already know, but you take explicit algorithm, this is simple algorithm, solve in time, and then keep on iterating in time, and that will keep on giving you some aspect of the interface. All right. So people, that's it. You are done. All right. Now, it turns out that there are various ways to solve this problem. You can take the whole problem the way I defined it, or if it is a 3-dimensional problem on a plane, you can do in 3 steps. So you can write in the direction, in the x direction, let us call it a star, you know, some intermediate. And this is again known value at n. This is not known, so you calculate this and plug it in here, and then you have double star, and finally the third direction gives you the final answer. Some people like to do this way. You don't have to, but this is one of the ways you can do it. And then there is what the people came up with is that they said that this is still is dependent on a little bit on the grid size and the Plick formulation, etc. So that is, you can do completely geometrically. So there were some people who then came up with a geometric construction, but the main idea is that you take the same terms. This is the equation, this is the convection term, and then you have it in 2 dimensions. I am showing you 2 dimensions, you can do 3 dimensions. You can again discretize the same way that we did on a cell, and you get this. Okay. Now it is written a delta A. Delta A is nothing but delta x times delta y. All right. So this is delta x. It is written for one-dimensional equation, and the delta y is built into delta A. Delta A is nothing but delta x delta y. There is nothing there fancy, it's the same discretization that we had before. But now you see the details of this, and so this is what is happening here is this is the I minus 1 cell, this I cell is I plus 1, and then this is gas, white part, and the yellow part is the liquid, and this interface which I am showing you in two dimensions as a straight line, it is moving with some velocity u. Okay, it needs to move, otherwise it's not going to change, and so it is moving. And so now what you want to make sure is that when it's moving, there is going to be change in the liquid versus gas. Okay, so when it moves, and it may not be at the same inclination, so what is going to happen is that the amount of gas versus liquid, that is the value of alpha, will change in time. All right, but you want to make sure that in this whole process, none of your conservation principle is violated. So now the same geometric concept which I showed you in a one dimension, you can do in 3 dimensions, and this is now the 3-dimensional plane. So now in 3-dimensional plane that you have as a triangle here, it becomes a little more complicated. So then you have the normal direction n, so the vector n dot r, which is the location from the origin, which must be equal to the distance, not a very big equation. So n is the normal to the plane, triangle, and r is some origin here, is the distance, and this must be equal to d. Now in 2 dimensions you can see more clearly here that this is the liquid, this is the gas, this is the distance d. This is nx and ny, and so then you can again discretize the way I did it. I mean, I am shown here in terms of alpha in 3 dimensions. So this is another way of doing the same problem. Okay, so there are 3 different methods I am showing you here. Okay, the first one is the main one that shows the discretization. Second one is that you can do in 3 steps, 1, 2, 3, x, y, z direction. Okay, so there are various ways to calculate it. If you like, you can only go back to the first one. Okay, so now if you go back to Fluent and you say that you know about it, tell me which method is used in Fluent. You use your own UDF? What? No, but but your own code VOF, what method are you using to solve the code? No, I mean, what I'm asking is the first one. So the Fluent also has the first one, but there are alternatives that I'm showing you here. Okay, so now what is the procedure? It is written there. If you want to follow it, just like I showed you before, calculate the interface normal, and then assign the cell type, and then this is more, for the 3-dimensional case. 1-dimensional case, only this much is enough, and then you can solve in the x direction. Same thing repeat in the y direction, and then you can do in the z direction, and you are done. So there is a various ways to calculate the same thing, but what is the difference between them is that one of them is better for conservation of alpha. So, I mean, the people have found in the experience. One of them is little less better. But if you don't want to worry about all these little bitty details about these fancy things, just go to the first one. And that is straightforward, and you can just code it in. And actually, that is, as far as I know, that is what the Fluent has. But maybe they keep on improving these things. But don't worry about that. So long as you know the first one that I showed you, this is good enough. I mean, this is okay. But you can use this and solve it. So this will give you alpha as a function of x, y, z in time. at a time t, t plus delta t, 2 plus delta t, that will lead to deformation. So, simply a convection equation, very simple linear convection equation that you need to solve, and solve it by explicit method. So, everything is known at the previous time step. So, if you have to guess a value of previous time step when you are starting the solution, what are these values? No, what are the values of alpha at a previous time step? Alpha n. Yeah, initial value. What is it? Hmm? You can you can just take 0. You can take 0 for gas and 1 for the other one. That is a standard way of doing it. Are you guys following what I am doing? That is correct. No, I mean, yeah, I mean, every time, whatever are you doing, whether it's alpha equation or any other equation, you want to make sure that you are able to capture the behavior of the bubble. So, the grid has to be reflective of that. Everything you do in CFD, you have to validate. I am not saying that there are actually solutions you can validate which have a simpler than bubble in 2 dimensions. You see that this one here shows if you don't have a very good grid, even if you have a Plick formulation, it will not capture it properly. Okay, and I will never recommend you to do this. So you have to have a reasonable grid. You just cannot get anything that you want. Suppose you didn't have this grid, you have an even rougher grid, and you have only 2 inclined lines. It will not give you a very good answer. No, as I told you that what is acceptable, you have to know about that. Just I told you that you have a circle and you can define in 3 points as a triangle. All right. Are you happy with it? If you are, it's okay with me. If you have 4 points, you have a rectangle. So there is a minimum number of points that can capture the bubble. Okay. And what is a minimum number of points if you are using a Plick algorithm? Okay. So that's why I was showing you here that suppose you had only half the grid of this, then you will have only 2 lines. Now, is that good enough approximation? That is the point. Now, if it is a good enough approximation, that's okay. All right. Now, also there are a lot of other tricks. I am just giving you the basic idea for a single bubble or single deforming phase. If you have in a particular problem thousands of bubbles, all right, you are not going to use this method. You will have to have a different type of approximation. Just like I told you that if you have 500,000 cold particles, you are not going to use the standard Lagrangian approach. You will never be able to do it. So if you have a problem that you have a packed bubble problem with thousands of bubbles, that one of the configuration I showed you, and you want to calculate that packed bubble, each bubble and how it will be, you are not going to do that problem by this method. This method is to understand the, let us say, bubble behavior where surface tension is involved. Okay. This method is not going to be used if you are trying to calculate some other goal is something different. Then you have to find out what is the best approximate way to do it. You understand what I am saying? Okay. So now, as I said, once suppose you have figured out and that you have got this information from that interface, then you go back to calculate your velocity field. Okay. So now you see it becomes whether it's a one-way problem or two-way problem, that will be very interesting. Because let us say it is a one-way problem, then you have calculated the bubble, and from the alpha equation, and then from that you can calculate the curvature, you know the surface tension, you know the normal, and you can plug it in, and then you have a one-way problem to solve the velocity field and the pressure field. But suppose it is not a one-way problem, it is a two-way problem. Then from there you calculate the velocity field, and then you have to plug it back in as a d alpha plus dt plus u dot gradient of alpha. And then you can iterate on that until they converge. So it becomes a much more difficult problem. Okay. So you will have to decide, what you should do. But in some cases, Fluent itself can decide for you depending on what exactly are the parameters involved, which means what are the forces acting on the bubble. Okay. If the forces are negligible, you can just ignore it. So, this becomes a two-way problem, but this alpha will give you this other answer. And so now you come back here, and again, it shows more details of it, that how do you calculate these terms in convection terms, etc., to make this, into that equation. All right. So, now it basically tells you the step about how do you really write the code. Now, what happens after the pressure gradient at this interface? Again, this is the term that is playing a role, delta p over rho, and these are again three scalar components. Now, again you do the same thing, that is, you have a cell-centered finite volume method, you calculate at the cell center, and then you have the interfaces defined, and then you can write this dp dx in terms of the cell-centered values, and then eventually you get the two values for the interface ij in terms of the cell-centered values I plus half and I minus half. And this is just a way to denote this, that this particular value at the center, it goes from face to the center, that is the interface value to the center value in these two steps, this plus this. So these are some of the details. I don't think this particular audience should worry about it, but you can read it if you want. But if you want to know the real implementation, then you can read the paper, original paper by Hurt and Nichols. But after that, a large amount of work has been done. So you are talking about a paper that was written 40 years ago. But otherwise, you can read the manual of Fluent and see what they have. Okay. I haven't read the manual of Fluent in a long time, actually. So I don't know whether latest version what they have. But it works, I mean, that's what I'm told, that is working. And these are the viscous terms that we already discussed. So it is a kind of repeat of what we have done before. All right. So this is the main thing, is that how do you incorporate this term, surface tension term. So that is where the more recent work that has happened in this area, that is in last, I would say, 10 years or so, that surface tension term in this equation, it looks like that if you do this, you have included it. So what is the trick here? You calculate the bubble, you calculated the normal from there, you calculated the curvature. What is the trick? How do you deal with the delta function? Okay, mathematically we know that as x goes to xf, it is 1 or 0. But in practice, your situation is more like this. Okay, or if you look at even the interface, it is like this. It is, can you define it as a sharp interface or a smeared interface? Okay, so that is where there is a lot of work, what is the effect of a smeared interface or the sharp interface, and that depends on the numerical scheme also that is being used. So that is where there is a lot of research that is being done actually in recent years, that how do you define that Dirac delta function, how do you treat it numerically. Mathematically we know that it goes to boom 1 and to 0, but how do you deal with it numerically, that is the question that comes in. So what is done there is that there are two approaches that are called in the literature. One is called the continuum surface force, and the other one is called the sharp surface force method. In the sharp surface force method, that interface is treated as a very sharp interface, which means that delta function is almost going to acquire a value of 1. But in the continuum surface method, it has a slight allowance of some continuity, which means it will transition not as a jump, but will transition in some smooth way. And that is where some fudge factors come in. Okay, people have some fudge factors to allow that transition, and there is no standard way how to do that, but a lot of experimentation, and a lot of experimentation means numerical experimentation people have done to see what those methods are. So it is written here that in the continuum surface force method, the surface tension is modeled as a continuous force and is included with a smooth delta function. If you, I don't know how many of you heard this word is smooth delta function, which means that the delta function is multiplied by some kind of first factor, so it doesn't just jump into 1, but it goes through some small. And the other one is that, so what happens is that if you use this method and keep on iterating in time, it gives rise to some kind of unphysical spurious velocity at the interface. So that is why when people started with this work, they used to use CSF, and they found that they were not getting very good answers once they kept on going. But that was the state of the art, so people said this all right. Well, I'm saying a reasonable grade. Okay. You can use always fine grade, but it's still on a fine grade. This can give rise to some smearing. But the second method then people came up with, and then they said that in the sharp method, the surface tension is implemented as a jump condition. So that means that it will completely assure that the interface is going to be a sharp interface. Okay. So now this is the term that we are interested in. How are you going to calculate on a grid this term? We have two methods we said. One is a sharp interface method, one is a CSF method. Let us say, just to focus our attention, that we are going to use the second one, the sharp interface method. Still you have this term. How are you going to calculate it numerically? I mean, I could have just said, you can calculate numerically. But the question is how it is really calculated numerically in the code. So what is done is that we basically say that this term can be represented just like a pressure gradient. Again, this is a formulation, that this is a best way numerically to treat with. No, you may argue it, that why pressure gradient, why not something, but this is the best way to treat it. That is, the numerical formulation of the pressure gradient is easiest in the entire momentum equation to treat with. So what you have is that you said, let us consider P dot. Now this is an artificial pressure gradient, by the way. This P dot has nothing to do with the actual hydrostatic pressure. I want to warn you, this is just a notation. You could have used some other notation. This is just a representation of this term in terms of some variable P hat. It has nothing to do with the pressure. The only importance of this is that it is treated as a pressure term just like this guy. This is a real pressure, and this is an artificial pressure due to surface tension that is here. The only difference is that this is treated like this in the momentum equation. So now if it is treated like this in a momentum equation and then you integrate it with the continuity equation, you can use a simple algorithm. Because then this becomes P plus P hat, and this is nothing but the identical equation that we had. And now we can apply the simple algorithm that I showed you before. So, in order to apply the simple algorithm, we are basically saying that this can be represented as this. Now, we have from the alpha equation k sigma, we already know nf, and then this one we can see whether we can treat it as 1 or we can have again a fudge factor in it. And then we say that now we can calculate this delta p from here, plug it back in here, combined with the continuity equation, apply the simple algorithm, and done with it. Okay. So, this is the numerical procedure that is being used, and I do not know whether it is described in that much detail in the Fluent manual or not. I am not really sure about it. So, in terms of the multi-phase flow, if you want to know some idea about the numerics, today's talk is the most important, which I have been telling you for last 2 days. And it is not comprehensive. In order to explain everything and how do you do that, I mean, you need a long time to digest it, but this at least gives you a platform that where to build it on. Okay. Now, this is the question that I think you were asking, that this is the interface and these are the grids, all right. And now these are this is a p hat, by the way. Remember, this is not p, this is this guy, surface tension. What happens here when you are trying to use it in the way we are doing the actual pressure? And you see, this is the interface. I am just, this is schematic, this is ij, this is I minus 1j. This is straightforward because this is in the liquid, this is in the liquid. But here to here, when you are going, you are crossing from liquid to the gas. How do you treat this particular term? Are you following me? Here to here, don't worry about it, it's standard. So, when you have this I minus plus half j, that is at this interface, no problem, ij, I minus 1j, done with it, because this is liquid. When you are going from here to here, you have this interface, you are going from liquid to the gas. What is the force that comes in? The surface tension. Surface tension. And so, this thing at this particular interface, this guy, I plus half gamma j, not only has this terms, but this is surface tension. And the surface tension kappa is coming from the alpha equation. So, this is how you calculate this at the interface. Once you have calculated this, is a straightforward, all right. Then you plug it in here, and now you are done, because now you have a very standard formulation that you can use the way we have done in the Fluent for single phase. Okay, but again I keep repeating myself, this P hat has nothing to do with P. It is a surface tension force. It is not the pressure force. It's just a notational convenience to show you that how it is done. All right. Yeah. Yeah. No, that part, suppose you have a circle, and if you are looking from this side is concave, other side is convex, that notation, that whether it's going to be on what side you take, that is defined very clearly. Okay. I am not saying there is a standard way, but the way the equations are formulated, it is clearly defined how do you calculate kappa. Okay, just give me a second. So, this is the most important part, that how do you integrate the effect of the surface tension, which has a delta function, into this equation. Okay. If you understood this part, I think that you have understood that how the volume of fluid method is put in numerically into the Patankar-Spalding simple algorithm for a multi-phase flow. So, if you go over what the notes I have given you, go step by step. I am not saying that you will understand everything, but I think you will understand a lot, and then you can always refer to the rest of the literature. Okay. So, now these are again the same kind of notations to show you, the left and right, I plus 1, how you define that. So, this is not that critical, to know. So, now this is the curvature that you are talking about. How do you calculate that? So, the curvature is calculated by this function for a curved surface, where the normal is defined by this function, and then in 2 dimensions you can describe is like by this. So, it will turn out that if you have a bubble and you want to calculate the curvature, tell me what is the answer. You have a bubble, right, and there is surface tension and it is in a liquid. You are going to use inside or outside? To define the curvature. No, I am just saying there is a bubble which is gas and it is surrounded by the liquid, all right, and there is a force that is exerted that way I showed you before, right. This is the force that is exerted. This is the force that is exerted, right. This equation that is written. How this equation was written, if anybody knows? The kappa in this case, the way it is, if there was a negative sign, then you come from outside. It is a positive sign, the way it is written is you go from inside. From the concave surface of the bubble, that is how it is written. You can change the sign, then you can do the other way. Yeah. You have to say that all the signs that we have are consistent. You see, why do you write minus delta p there? What? That is the reason you write delta p. Yeah, that is the reason you write delta p. From have you seen how you derive the fundamental Navier-Stokes equations? Why the delta p is negative? Huh? What is that? It means that all the answers that I am getting, it means that you really don't know how to derive the fundamental equations of fluid mechanics. The answer is any object that you have, whether it's a fluid or it is a solid, like my head, right? How is the pressure acting? The pressure always acts normal to like this. It doesn't act like this. No, no, no. Don't justify. The answer is only one, and that is it acts like this, it acts like this, it acts like this. And if you assume that the pressure on a fluid element here is acting like right. If you have a fluid element here, first of all you have to know that the pressure is a surface force. Viscosity is a surface force. Surface tension is a surface force. What kind of force is gravity? It's a body force means volume force. So this is a surface force acting here. Whatever you try, unless you want to violate the law of physics, it will always act like this. Pressure always act like this. This may act this way, viscous force. Surface tension may act one way or the other, depending on the pressure difference. But the pressure will always act like this. Then if you do the fundamental formulation of Navier-Stokes equations or Euler equations, it will no. The normal is like this. Yeah. So the answer is that the pressure always acts normal to an object or the fluid element, and the normal to that fluid element acts in the opposite direction. And so that is the fundamental mathematics that gives rise to gradient of P. And why you have a gradient of P instead of delta dot P? Because it's a scalar. It's a scalar. It's a scalar. So similarly, if you use the argument that how is it a surface tension will acting on a curved surface, whether it's a positive or negative, will give you the right sign. Will give you the right sign. You understand what I'm saying? If you take this bubble and you see how the curvature should be to get the pressure difference. So for a bubble to exist, tell me whether the pressure inside of the bubble should be higher or the outside should be higher. So you already know the answer. So the pressure inside should be higher to sustain the force of the surface tension. So in order the pressure to be high inside and have to be lower outside, what is the direction of the force? Outward. So what should be direction to balance that force of the surface tension? You got your answer. So what I am saying is that I keep on emphasizing, not only to you, all my life I have emphasized to the student, think physically. And then you will have the answer rather than trying to play with the mathematics, this is happening, that is happening. You got your answer now? So that is what is going on here by having a plus sign. Now nobody is saying that you don't have a minus sign, but you are unnecessarily causing problem for yourself. Of course, if you put a plus sign here, I don't think you deserve to be a fluid dynamicist, because you are basically violating the fundamental law of physics, because the pressure cannot act the other way. This is by the nature that the pressure will act the way it acts. Okay. Now you may say, well, I can do it mathematically. You know how? Pressure will act the way it is acting, but I will start defining normal the other way. Instead of defining outside, I will define inside. Then you will screw up the entire mathematics. You see what I am saying? So you remain consistent with the knowledge that people have generated over hundreds of years, and then keep the equation. You will not find a single book which will have a pressure term written plus here, because the convention is that normal should always be normal outward, and the pressure you cannot change because the nature has made it that way in that way. So that by that way you have minus delta P. You see what I am saying? So you don't want to now you can insist, sir, I am going to have my normal the other way. All right. So what you are doing is that you are screwing up all the textbooks and everything, right? And also whomsoever you are teaching, you will be messing them up too, right? Now don't be offended, I am just trying to be, yeah. No. Now you are saying it correctly, but initially you were saying flowing from Monday. Okay. So, this similarly you already got the answer, that what should be the right answer if you are writing the force in this fashion, whether it should be a convex or concave surface. Now, if you have a concave surface, convex surface, you can make it negative. There is no problem. Okay, because surface tension, just like the shear force, has the flexibility. It can go this way or that way, the way you define it. Like in shear force, on a cube or in a fluid, has two directions. Okay, it's this direction, that direction, and what does it depend on? The shear force is depending upon which direction you are applying the shear. So, if you don't like, if the problem is such that you have to applying the shear this way to deform, it's okay. You're applying this way, there are 6 components, you can do that. But pressure, you cannot do that, because God has said that pressure has to be this way. So, you cannot play around unless until you change the entire mathematical convention. And similarly, surface tension, you can have a flexibility of changing the direction if you want. Okay. So, this is the expression, and you can go over that, and then it is written in the whole methodology. In every case, step 1, step 2, step 3, you write down your own code. If you want to write down your own code, you can write your own code. And then there are some other methods, I don't want to go into those details. If you have a lot more complication, and you can write down your own code, there is enough information, but I would say that to write your own code, you should gather even more information. But there are steps that you can use. All right. And so these are the complete solution steps that you have to do to go through this calculation to determine alpha n plus 1. All right. So I will not go over this. A complete solution step that I already have done for you, and then you can look at it and go over it. I think that there is no point in belaboring this, because this basically is nothing but the application of the procedure is the same as for the Pattankar-Spalding algorithm. Because what you have done is that you have taken this delta function term, apply the sharp interface method, taking the approximation to write it as delta p star over rho. Okay, again, please don't confuse that. It is not a pressure, it is just a convention. And then you have p plus p star, you have the total term. You can then use the momentum equation, continuity equation, apply the algorithm, you are done. And now you have incorporated the volume of fluid method into the Navier-Stokes equation. Is it clear? This is a very important part of this whole course. So if it's not clear, please raise your hand, and I'm willing to spend as much time as required to clarify some of these statements that I've made. Yes, sir. It will take care of the deformation of the bubble. No, we have not discussed the issue of bursting. Okay, so the bursting phenomena, etc., you have to do some more approximation. Okay, now people can do the bursting, but then they have to do some special things that you have to put in the algorithm. Now, when does a bubble burst? Suppose you have a bubble, right? Under what condition it will burst? Don't think about any mathematics, just physics. So the pressure is larger than to be able to balance by the surface tension. So if you suppose you are doing these calculations, and in the process of VOF, etc., it turns out that some bubble got generated, then you have to put some kind of a condition inside the code. I am not totally sure how it is done, but that it burst. So when it's burst, then that became a gas, right? And so it will add some gas to it. So now if you have thousands of bubbles and all of them burst, what will be the effect of it? So you can add the complications that you want, And I don't have answer for all your questions, but these are the kind of things that you might put, but I don't see how that you should be able to do it. That's why my feeling. But how much complicated it will be, how are you going to incorporate in the code, I don't have a clear answer for you, because I myself don't know at this point. But this is my conjecture and this is my feeling that there should not be a problem. I think that may require some other considerations, that under which circumstances the coalescence will take place. So it means you have another bubble here, your other bubble here, they have to hit each other, and then the hitting impact, there has to be a hitting model there. So if there are bubbles, they are called the soft sphere model of collision. If you have cold particles, they are called the hard sphere model of collision. So you have to then have those models of collisions are there, which involve some other properties of collisions, and then you have to see how those models will play out, how do you integrate into the code. So all those things can be done, and they have been done. It is not that they have not been done. There are people who have already done the collapse of bubbles, hitting of the bubbles using some soft sphere models, and they continue to develop it and continue to improve it. No, it can be different. People have done this, and it can be different. And also, as I said, to keep it simple, they should be the same. But if you want to add the complication, they can be different. No, it's a vector U. And so you can also split. You can have additional equations if you want. So all kind of complications can be added. But right now, you see, the whole purpose of this talk is to keep it simple enough that you can get some ideas. Okay. The whole purpose of this talk is not to make it so complicated, then we get lost into things that even the basic is not clear what's happening. What is that? No, we are not considering in this presentation. As I told him that we are not considering in this presentation. But it is possible to do it. But in this presentation, it is not being done because we want to just keep the idea simple enough so that you know what exactly is being. I don't know. But I don't know that if they are different, the fluent can solve it. So it must be that it's being considered. But in this presentation that I have, it is not being considered. The goal of this presentation is that what the V of a method is, and how do you solve this method, how do you numerically integrate this method into the momentum equation so that you can apply the simple algorithm. So that is the only focus we have. Now if we add more complications, like if we have two-way coupling and some other stuff, then I think that you can keep on adding and you can make the whole thing complicated. But I don't see any reason that why it cannot be done. Okay, but the presentation, the way I have made it, that my main goal was just to give you some essential elements that how a VOF method is integrated into the standard simple algorithm by accounting for the effect by using the surface force method rather than the continuous surface method. So I at least cover actually a lot more than what I was intending to do, to see what is the best way you can have a one-way coupling to calculate the interface. Okay, but if you are having other additional things that you are asking or you are asking, I don't see why it cannot be done. I don't see that what is the complication that may arise. The only complication that may arise is that you may have additional equations, additional terms to allow for all these additional kind of effects of different velocities, etc. But the fundamental way you will solve the VOF equation, there is not a unique way there either. I am sure that somebody else may come up a different way to solve the VOF equation, integrate it not in a Pattankar-Spalding algorithm, but in some other algorithm. So that is an all open area that you can come up with some new ideas for new algorithm. But our focus is to just concentrate on the most widely used solver and what are the basics of that to do this. For example, if you do even the simple algorithm is not used anymore, right? You have simple C and you have piezo and you have this sophistication and that sophistication, right? But if you know simple, that is good enough to know everything that is there at a fundamental level. So if you know the VOF that I am explaining to you and how it is integrated into the simple algorithm, you will almost, I can guarantee you will not, you will have the knowledge of that 90% of the way it is done. Okay. Alpha is equal to 1 and 0, both are permissible. And what will happen is that if you put in, you don't have to even do the integration. You go to the basic level, then you will say that there is no need. These equations will drop out. This equation will drop out. And they are very good questions actually. Any other question? Yeah. No, you don't have to do. You can just take the whole fluent as a black box, and if you know how to use that black box properly, and you become very good at it, that means that you know how to grid it. You know what kind of concentration you have. You know that what is your goal. Then you can say VOF. You can say this. I will show you tomorrow. Let us say the calculation of a droplet hitting a ground. We did not. The person who did it, my student, I don't think he went into so much depth. You can do it. The purpose of this is that at least you should know a little bit. A little bit. Like I use Microsoft, okay. I don't know what is inside. Okay. So long as I can type my equations, I can type my stuff, I can make a PPT, I can do everything very nicely, I am happy. Okay. I don't have to know that what is in Microsoft. Okay. And even if I tried, I will not be successful. But you guys need to know, because you are a CFD expert, you are a fluid dynamics expert, you want to do you have to know a little bit. I think it is inexcusable that you are a fluid dynamicist and you don't know the pressure acts normal to the body. Okay. Your answer should be so precise that you don't do this wishy-washy thing. These answers should be very precise, that you know the fundamentals of fluid mechanics. No. If something goes back, at least you should do the stuff that you are using. Now, like VOF, you should at least know what VOF means. You should know at least a little bit that what does really VOF do. Yeah. If you don't know it, I think you can still do some calculations. I am not saying you cannot, and you can get away with it. Maybe I am telling you that I have come across people in my career who prefer to have a blind eye and try to use the software as quickly as they can and get the answer, and they're happy with it. I mean, it's okay. As far as I'm concerned, it's okay. But if my preference is there, I would like them to, at least for their own satisfaction, know a little bit how it is. When I say VOF method and I ask a question, simple question, and a person says that I am multi-phase flow expert, I say, okay, this VOF method, even if you don't know the details, let's forget about it. How it is integrated into simple algorithm. 99.9% people cannot answer. I want them to be able to answer that question, that how the VOF method, the surface tension term, is integrated into Fluent so that you can still use the simple algorithm. Okay. Now, as I said, this whole presentation that we are doing today, I mean, you can spend the whole semester actually going over in a finer detail, but this is good enough for, because we don't have time, this is good enough for you to know that such a thing exists. You can go to the literature, you can explore, you know, the papers, you can explore the books, and then, you don't feel that, you are reading something that, uh, that is really a problematic thing. Because if you understand, whatever is being taught and you are paying attention, I can guarantee you that this is good enough to really call yourself at least a person who is knowledgeable in multiphase flow, if not an expert. Okay. All right. Any other question? All right. So, yeah. Let me ask you this question, that anything that is going to take place at the interface, whether you want to call it a shear or you want to call it a pressure force, on the interface, there may be a shear, right? There may be a pressure force, there may be a surface tension force, right? They are all included. These equations have everything in it. So now, how it is going to manifest itself, it will depend on problem to problem. Pressure, viscous, gravity, surface. Okay. Let me ask you a simple question. Let me ask you a simple question. You have, forget about interface. You simply have a ball, some sphere, and the flow is flowing. Just a cylinder, basic fluid mechanics. Flow is flowing. I have a question. How is the viscous shear stress, which is a tangential shear stress, is going to take place? How do you calculate that? if you have a ball and the flow is taking place, and I am asking you calculate the flow field, pressure and velocity. Now, pressure, the tangential shear stress on the ball. That is a question I am asking. How are you going to calculate? Hmm? I think that I am really frustrated. I am really frustrated. You have a ball and you have a code, right? Fluent. That's what we are talking about. You have a ball, and I told you it's very simple circle, cylinder, and this is a fundamental problem in fluid mechanics. And I said calculate the flow. Okay. Now it will calculate pressure and velocity, right? Rest are all derivative quantities. Once you have the velocity, you can always calculate the gradient. Once you have the gradient, you always calculate tau, right? Right? How do you calculate the velocity and pressure? Yeah, that's it. That is the whole thing I am preaching for 1.5 hours. No, I don't want to listen to you. You are not thinking correctly. I am still not thinking correctly after my speaking to you guys this morning. You have a ball, right? You want to calculate shear stress. How do you calculate shear stress? You want to calculate the pressure and velocity field with the boundary condition creating the grid, right? How do you calculate that? All the right. Now, in your case, at the interface, you have a surface tension force. From the surface tension force, you can calculate all these equations and everything in it. These are derivative quantities. So, shear stress is derivative quantity. If you want to calculate the pressure, it comes out directly, pressure and velocity. But shear stress is du dy, right? You use that. If you have heat transfer, what is that? It's a derivative quantity. You calculate the energy or temperature, and from there you calculate dt dy. If you don't know that much of fluid mechanics, and then you are saying that you want to learn multi-phase fluid mechanics, there is something fundamentally wrong the way you are thinking. He is asking me that how do you, the interface pressure, there is a tangential stress going on and all that. Once you have the entire flow field, you can calculate any derivative quantity, whether this tangential, that tangential. You only need to know the velocity field and pressure field. That's it. And everything is built into your equation. If your boss asked you that calculate the shear stress over a car, and you will say, sir, I have to calculate the gradient, I have to do this, I have to do that, you are not thinking it straight. Are you getting my point or not? If you want to calculate directly the shear stress, right, tell me which code will calculate directly the shear stress. It means that you will have to formulate the whole Navier-Stokes equations by treating the shear stress as a unknown, right? All right, you will discover new fluid mechanics. I think the fundamental problem is that the way you guys are thinking how to solve a problem in fluid flow, unless until that problem is resolved, the next step would be to how to use the tools. But if you are not sure about how to calculate, how to solve the problem by using what is the problem that you are solving, and you are going in all over the place, right? I mean, you want to go from here to the Prayagraj station, right? Right? And you are going all over the place. It's better to use your calculator, that cell phone or a GPS. It will take you directly where to go, right? Otherwise, you will be lost. I mean, you are going to go this. That is what you guys are doing. Once you have solved this equation, it has everything in it. If you are close to the interface and you know the velocity field, you know the pressure field, you know everything about the interface, everything. You take the gradient in this direction, you get the tau. In this direction, you can take exactly the gradients or whatever you need, the shear stress, exactly at the interface, and you will give a calculation. I think he is still confused. No, if you are confused, it's okay. You can admit it, there is nothing wrong with that. Because these things will take time to figure it out. I mean, you have to read all this, you have to see what I'm saying and how, you interpret it. The main focus in multiphase flow here is that how to account for the effect of surface tension using the VOF into these equations so that you can apply the simple algorithm. And all the quantities that you are getting is U, V, W, and P. And once you have a U, V, W, and P in the entire field, you have everything that you want to know. And if there was a temperature or a heat transfer, then you get T also. Then everything you want to know is there. You can create non-dimensional numbers if you like. You can create a bound number. You can create the Weber number. Because you have all the information that you need to basically plug it in. But if you are thinking that I want to calculate the tau on the flat plate directly, then the only thing you can do is by experiment. I don't know how to do it numerically. Because numerically we don't have the conservation equations written in terms of tau. If somebody was asking MHD, right? Suppose you want to add MHD, I had one problem that I showed you with MHD, the steel ball, the bubble in a steel metal. Same equation. What do you need to do there? This is surface tension, right? This is gravity, this is pressure, this is viscosity. What do you need to do? Add the Lorentz force. That's it. And then you want to know how does the Lorentz force affecting the velocity field, it will give you the answer. If you want to know how the anything else is affecting, it will give the answer. Okay. Any other questions? Yeah. One thing I want to know, how do you convert a surface force into a volumetric force? No, I just want to, I don't want to talk about mathematics right now for a moment. I want to ask you, physically, God has created some physics. Physically, how do you convert a surface force into a body force? How do you convert the pressure into gravity? Gravity like force. I want to ask you. No, no, you are sitting here, right? There are two forces acting on you. You know what they are? Hmm? And pressure and force. Your pressure is acting on your surface of the body. All right. Can you convert into gravity and increase your weight? Physically, if you are right, the pressure that is acting on your body, you can integrate it, right? You have a surface, you have a pressure, right? That is what we do in calculating the flow over a wing to get the lift, right? Or anything. Just consider yourself, you're sitting, you're not flowing or anything, you're sitting. You have pressure. By any integral method or any method, you can calculate the total amount of force on you, right? And you go and sit down in a balance, you know how much weight you have, right? Right? I don't know how much you have, maybe 100 kilogram, right? Okay. Don't mind if you are, less than 100 kilogram. All right. Okay. Just I'll give you a number. Okay. Now, no, but I'm saying because you might like to correct me, hey, no, I'm not 100. But anyway, if you are, if I believe your theory and you have this force acting, I know that your force is acting on you because of pressure. So your total weight, if it can be converted into the body force, then your total weight will be the pressure of the body plus your mass that ever you have, that should be your total weight. All right. I don't want to care. I want you to first think clearly. No, no, I don't. I know what you're trying to tell me. I want you to think clearly. First, think the physics. Is it possible? No, no. Answer my question. Is it possible to convert a surface force? No, no. Don't argue with me. I know the premise. I already understood what you are trying to say. I am trying to take you there in a logical way. I know what exactly you are asking. Don't think I don't know. Yeah, I don't want to give you the answer until you have agreed to me with me what I am trying to say. Then I will answer your question. No, first you answer my question. Is it possible to take the surface force and convert it physically into a body force? Answer my question, then I will answer your question. You're taking too much time. No, no, you are taking too much time. I mean, it's sad. If you don't know, it is really sad. Don't mind, when I am making this statement, it is no personal attack on you. It's just a conversation, a friendly conversation. Okay. I don't want to say that I'm, it's okay. I don't want to use that word because you are totally wrong. You should not have taken a second. You cannot convert a surface force into a body force, whether it's a viscous surface force or a surface tension force or a. Now, MHD force, Lorentz force, what kind of force is that? There's some MHD guy here. What kind of? It's a body force. It's a body force. Gravity is a body force. You cannot interchange these guys. Now, I know what you're saying. You are saying that when you are deriving the Navier-Stokes equation, then you apply the Stokes theorem, right? And that Stokes theorem converts the surface integral into a volume integral. And that is how you derive the Navier-Stokes equation. Because what happens is that delta P is written as P dot P n times ds, and that integral you convert into gradient of P times dV as a volume force, so that you could combine everything and you can say that everything is a volumetric term and throw them away, the integral. Forget about natural convection, just talk about Navier-Stokes equation. Yeah. Keep life simple, okay? No, we were just, as we are just talking about, you agreed with me. And no, wait a minute, listen to me now. I don't want you to interject. That pressure force is a surface force, but gravity is a body force, right? So it means that when you are writing the mass times acceleration is equal to the forces, that is Newton's second law. So the mass times acceleration is your convection terms in Navier-Stokes equation, right? And then the right hand side, there are three types of forces: Fp, surface force; Fv, viscous force; rho g, gravity force; and surface tension, if you want to consider that, or Lorentz, or whatever it is. They are all surface forces. How do you write the integral form of the equation that you have? Integral form. No. Listen to me. For the volume that you are considering, that volume has some surface. The integral form you have, there is a momentum term, integral form. But the momentum term also is a surface term. Only the rho terms, the first one, all right, that is the term, that is a time dependent term, which is a volume term. Everything else is a surface terms in the momentum equation. You agree with? Because momentum in and out of the surface. And then the three force term. In order to have it from an integral form, if you kept the integral form, you can calculate the surface. You can have a numerical algorithm where you use the surface. But you want to make it a partial differential equation. It turns out that there is a Stokes theorem that can convert the surface integral into a volume integral. Okay, divergence theorem, Gauss theorem, okay. That is what I meant, all right. So now you have that which converts this to this. Then you have everything in the volume integral form. Then you can throw the integral, assuming that there are no singularities, and you get the partial differential equation of Navier-Stokes. Don't bring Boussinesq and all that right now. So what happens is that P times the vector n becomes dead gradient of P. And the V in the momentum terms become delta dot rho VVV tensor, right? Now that mathematical trick that you did to get the partial differential equation, it did not change the nature of the force at all. The nature of the force is God given to you. Now you are saying that you take these equations which are written by removing the volume integral, and that you want to keep those integrals as the surface integrals. Do it. I don't have problem with you. Yeah, you can do it. But at this stage in life and using the fluent, if you want to do that, it's up to you. You can spend another 20 years. No, no. If you want to make, the reason people do this thing, and they have spent so much lifetime, so that life becomes simpler. If you want to go back and make the life more difficult, I have no problem. You can go there. I have no problem with you. So what you're saying is that you take this, you convert, you put the integral form of it, you take the volume integral, convert into surface integral, and then solve some of the term with the surface integral, some of the term as a volume integral, and then you have to take into account this funny, all these things are going around, then all this mesh business and everything will go down the tube. So you are making actually life very difficult by having a combination of surface integrals and combination of volume integrals, and then you have to figure out how to use the mesh to have these two kind of integrals and then have make sense out of that. Does it make sense or not? But please don't tell ever to anybody that you can change the pressure force into a body force, because mathematically it's possible. No, mathematically you can do it, but physically you cannot do it. The way you do it, send me email. I will give you a $1,000 check right away. No, don't make life more complicated, It's already complicated, right? But I like this kind of question because it makes the life, very interesting. Our conversation is good. We have a good conversation. We have some humor. We have some fun. Otherwise, it is a very dry subject. You know, it is not like cashews. No, he is a good point actually. I like what he said. Now everybody understands that how are we accounting for volume of fluid method into this, right? And I think that uh, it is not possible today to cover all this that I have, and particularly I wanted to cover Eulerian and all this other within the simple framework, and after that I really wanted to cover IPSA algorithm and then the LS, the level set description. At least give you again a flavor which is in the fluent and which is even more difficult than the VOF that we went through. Okay, so in order to avoid a heartburn for myself, maybe I should skip it. But I think it's so important that instead of continuing today, which is not possible, it's already 8 o'clock. That I think we will spend again tomorrow and go over, because this is the heart of the whole course.